Okay, so imagine you've got a pile of coins. Your mission, should you choose to accept it, is to arrange them into a perfect staircase. Now this sounds like a simple little brain teaser, right? But it's actually a fantastic way to understand two totally different and equally brilliant ways of solving problems. So today, we're going to dive into this puzzle and explore those two very different paths to the same answer. Let's make this real. Let's say you have exactly 8 coins. The rule is super simple. The first row gets 1 coin, the second row needs 2, the third needs 3, and you keep going like that. So the big question is, how many complete rows can you actually finish before you run out of coins? Go ahead, pause, and give it a shot. It's a fun one to puzzle.
All right, let's walk through it. We're starting with our 8 coins. Row 1 takes a single coin, so we're down to 7. Row 2 needs 2 coins, now we have 5 left. For row 3, we use 3 more coins, leaving us with just 2. Now we get to row 4, and it needs 4 coins. Well, we only have 2, so we can't complete it. And that's our answer, 3 complete rows. Simple enough, right? But what if you had, say, 1 billion coins? Counting like this is just not going to cut it.
And that brings us to our first path, our first way of thinking like a mathematician. See, instead of just counting step by step, a mathematician is always on the hunt for a hidden pattern, some elegant formula that can solve the whole thing in one shot, no matter how huge the numbers get.
And it turns out there's a beautiful pattern right here. The total coins you need for k rows is just 1 plus 2 plus 3, all the way up to k. You might recognize this. It's a classic arithmetic series, and it has this super neat formula. K times k plus 1, all divided by 2. This little equation is our key. It tells us the total coins needed for any number of rows.
And just like that, our fun little coin puzzle transforms into a math problem. All we have to do now is find the biggest possible k, our number of rows, where the result of that formula is less than or equal to n, which is the total coins we have. The entire game is now about solving for k.
This, right here, is the power of that mathematical approach. You take that inequality, you rearrange it, you solve the quadratic equation for k, and you get this single beautiful line of code. This is the direct answer. You can plug in any number for n, even 1 billion, and bam, it just tells you the answer instantly. No counting, no loops, just pure direct calculation. It really is kind of like magic.
But what if you didn't spot that mathematical trick? You know, maybe algebra isn't your favorite thing. And that's totally okay, because there's another path, a whole different way to look at this. And that's by thinking like a programmer. This approach isn't about finding a magic formula, it's about creating a really clever process to find the answer.
The philosophy here is fundamentally different. It's, okay, maybe I can't calculate the answer in one step, but what if I could just search for it? We know the answer's in there somewhere. We just need a smart, efficient way to find it without having to check every single possibility one by one.
So to do that, first we need to define our search space. What are the boundaries? Well, we know the answer has to be at least 1 row, right? And it can't possibly be more rows than the number of coins we have, n. So the correct answer is definitely hiding somewhere between 1 and n. The challenge is, how do we search that range without wasting time?
And the perfect tool for this job is called binary search. Seriously, think about how you look for a word in a dictionary. You don't start at page 1 and flip through every single page. No way. You crack it open somewhere in the middle. You see if your word comes before or after that page, and just like that, you've eliminated half the dictionary in one move. You just keep repeating that process, having the problem again and again until you zero right in on what you're looking for.
Let's see this in action with our 8 coins. Our search space is from 1 to 8. We guess the middle, 4. How many coins for 4 rows? Well, that's 10. Oops, too many. So we know the answer must be less than 4. We can throw out 4 and everything above it. Our new search space is just 1 to 3. Let's guess the middle again, 2. 2 rows need 3 coins. We have enough. But, maybe we can do better. So we check the upper half of our remaining space, 3 to 3. The middle is 3. 3 rows need 6 coins. We have enough for that too. And since there's nowhere else to search, we've found our answer. It's 3.
So there you have it, 2 totally different journeys, right? One was this flash of algebraic insight, the other was this methodical, logical process, and yet they both led us to the exact same answer. It just goes to show you how you frame a problem can totally change how you end up solving it.
This really is a tale of 2 different mindsets. The mathematician is looking for that hidden equation, that one elegant shortcut that cracks the whole thing open. The programmer, on the other hand, sees something different. They see an ordered, searchable problem, and they reach for a reliable, step-by-step algorithm to hunt down the solution inside a well-defined space.
Let's break it down a little more technically. The math formula is a direct calculation. In computer science terms, its efficiency is O of 1, or constant time. That means it takes the same tiny fraction of a second whether you have 8 coins or 8 billion. It's basically instantaneous. The binary search is an iterative search. Its efficiency is O of log n, which is still ridiculously fast. Because you're having the problem every time, finding the answer for a billion coins would only take about 30 guesses. The core insight for the math solution was seeing the algebraic relationship. For the programming solution, it was spotting the monotonic property, the fact that as you add more rows, you always need more coins. That's what makes a search like this possible.
So why are we talking about all this? What's the big deal? Well, because this one little puzzle gives us a much bigger, much better problem-solving toolkit. It's not about which method is better. It's about knowing that these different perspectives exist and knowing which tool to pull out of the box for the right job.
You know, the real lesson here is this. An elegant solution can come from a sudden flash of insight, for sure, but real power also comes from a reliable, systematic process. A great problem solver doesn't just have a hammer. They have a whole toolkit. They know when to hunt for that clever shortcut, but they also know when it's time to build a methodical machine to get the job done. Ultimately, the goal isn't just to find an answer, it's to understand why it's the answer.
And that brings me to a final question for you. Now that you've seen both of these paths, which one feels more natural to you? Do you find yourself instinctively looking for that hidden formula, that elegant shortcut? Or do you gravitate more towards building a solid, reliable process that's guaranteed to search and find the answer? There's no right or wrong here, but knowing your own natural inclination, that's a huge first step toward becoming an even better, more versatile